Let's see. So, we're going to be talking about. So, matrix coherence is something that's gotten a lot of attention. It's slightly different things to different people. But I'll be talking about how to compute it quickly. In fact, you can get an awful lot more using the Bayes technique, including a whole suite of things I'm going to call statistical leverage. So, let's let A, just to set notation, A be your n by d matrix. And I might have a slide later where I slipped to m and n, but n by d matrix. N, it's tall. N is large, D is small. So we're dealing with a tall matrix. All right? The idea is we'll extend to fab matrices, it will extend to streaming environments, they'll extend to L1 based penalties instead of just L2 based penalties. For the moment, I'll be talking about it in this more simple context. All right? The statistical leverage scores are the diagonal elements of the projection matrix onto the left singular vectors of A. So if A is tall, its left singular vectors are tall. All right? You have a tall matrix. The columns are unit length and orthogonal. The rows are not. Right? This could be a bunch of columns from the identity. This could be a bunch of columns from the atomar. So these row lengths could be very uniform or very non-uniform or anything in between. And the coherence of the rows is the largest such score. All right? Sometimes coherence means the largest off-diagonal element of that projection matrix, which is equal to not the largest Euclidean number of the rows, but the largest dot product between two rows. So what I'm saying we'll go through for all of those. So the basic idea of statistical leverage is that it's going to measure the correlation between singular vectors and a matrix on the canonical basis. Intuitively, it gives you how much influence or leverage each row has on the best least squares fit, or intuitively where in the high dimensional space the singular value information is being sent, not what that singular value information, or sort of relatedly, the extent to which a data point is an outlier. All right. Now, it's always good to ask who cares. So you might not, given the slide, you may or may not know that you probably do care, actually. All right, so this is probably something that touches what you do. So in statistical data analysis and machine learning, these are the diagonal elements of the so-called hat matrix, used in regression diagnostics for measuring how much a data point is an outlier. Did you kick the machine when the data was generated and just have a total outlier or not? Recently, the Nystrom method, matrix reconstruction, a whole slew of these things typically assume that these scores are flat. They're parameterized in such a way that you need to sample k log k or d log d or something like something times the coherence. All right? Now, if the coherence is small, that's not bad, right? And of course, it's an empirical question as to whether the coherence is large or small. In empirical fact, if you look at any of a wide range of data, from biological domains to internet domains, wide range of data, is that they're wildly non-uniform. All right, so that's a little disconcerting in that the theory assumes that they're flat. So if you do this, you should care. Numerical linear algebra. There's been a huge range of work on randomized algorithms for matrices, and you heard about some of this earlier. This, understanding the role of leverage here, is the key structural bottleneck for making those algorithms practical. All right? Roughly, if you want to do random sampling algorithms, you use these as an important sampling distribution to sample with respect to. And if you want to do random projection algorithms, you rotate to a basis where these things are uniform. All right, I did work in theoretical science before these things were useful, and practitioners in data analysis and numerical linear algebra did not pick up on this. It was only when Breneus and I deconvoluted the randomization from the structural linear algebraic properties, in which case these sort of scores pop out, that these algorithms were implemented by numerical analysts and used in machine learning and data applications. Theoretical computer science. This was a key structural non-uniformity to deal with in worst case analysis. So these are the very sort of statistical things. These are the key non-uniformity that you need to deal with. Either find and sample or wash away with a projection. So, how do you compute these things? Do SVD or QR. Takes high dimension times low dimension squared time. N times D squared time. So do QR or SVD to get a matrix Q and evaluate the Euclidean norms of that Q. That takes N D squared. Low dimension times high dimension times low dimension squared. We're going to want it faster. So little O of ND squared. Either faster in theory or faster in clock time, or little O of orthonormal basis if you have a square matrix, with no assumptions whatsoever on A. So how do you do this? So the main idea is extremely simple. So if you like sort of gratuitously complicated results, you're going to be disappointed here. If you want an extremely simple result, this will be it. Now that's not to say it was easy. It took us 5 years to find. But once we found it, it's extremely simple. So the main theorem is going to be, given the matrix setup I had, we can return all n diagonal elements of this projection matrix. And we can get all to relative error, and we can get all large off-diagonal elements to additive error. The problem in all these applications is when things are large, because you can replace you have this distribution that you get with 1/2 this distribution times 1/2 uniform. So this is actually relative error if these things are very non-uniform, but we can find all the large ones. And we're going to run in little o nd squared time. What that means is it's nd log d time. All right? And for very modest sized matrices, you know, a couple hundred by a couple thousand, you're faster if you have a good numerical implementation in plot time. I'm not going to have time to go over. We actually have an implementation. You can put the stuff on Amazon EC2 if you ever want to parallelize over 8, 16, 32, 64, and so on processes. All right, so let me take an aside. And if you understand this, you'll understand 95% of the work in randomized matrix algorithms, including how to compute these scores. So change the problem slightly. I've been promising you we'll do the leverage scores. Slightly different problem. Over-constrained least squares. Again, A is still tall. Minimize AX minus B. The solution is do QR or Cholesky or whatever, SVD, to compute this X opt. Right? N times D squared time. How do you do it faster? Here's an algorithm that's not faster, but if you understand what's going on, you'll see how to improve it. So, for I equals 1 to n, compute the leverage scores. Exactly or approximately. Randomly sample a small number of constraints, using that as an important sampling distribution. And solve the subproblem to get x hat opt. If you solve that subproblem, you're golden. So don't worry about gamma, it's a fudge factor. You get ax minus b is less than 1 plus epsilon times the exact answer. So your relative error on the objective. And the difference between x opt and x hat opt is epsilon times the condition number in some fact. Right, so your relative error in both senses, very strong senses. Unfortunately, the naive algorithm here takes n times d squared time. So I've given you an algorithm that's no faster, might fail with some probability delta, and is epsilon worse. So that doesn't really suggest a lot for itself. But it can be improved. I'll tell you how to do that. And this is a key bottleneck in not only squares implementations, but a whole slew of low-rank implementations. The random projection algorithms you heard about. So, how do you make it fast? You either do a random projection. When you do a random projection, you rotate to a basis where the leverage scores are uniform, up to logarithmic fluctuations. Then you don't need to compute them, you simply uniform them. Or, approximate the leverage scores. All these things are robust. You don't need the exact scores. I can give you 2 approximation, a 1 plus epsilon approximation. And that's how I'll tell you how to do that. So, under constrained, I described over constrained. Similar results go through to the under constrained least squares problem, perhaps not surprisingly. So, back to approximating leverage scores. View the computation of the leverage scores in terms of some different under constrained least squares problem. So recall, if A is n by d and n is tall, consider this problem. Take every column of A and get the best least squares fit to the ith column of A. Clearly there's a solution to that, right? You return the ith column. That's not the best solution in a Euclidean norm sense. The best solution, X transpose, is given by this EI times AA plus. All right? But PI, which is the leverage score you want after some scaling, but PI is equal to EI, the canonical basis, dotted into U. It's the Euclidean norm of that row. You can add that without changing anything, so it's EI dotted into this. But this is a projection matrix. And if I want to make my life difficult, I can write that projection matrix this way. So the leverage score is equal to the Euclidean norm of that of this quantity. Or equivalent, I can relate it to this under constrained least squares problem. So what I do, I say Pi is equal to the I element of AA plus, or the ith element. Now this is expensive to compute, but if I wedge a random projection in there, a fast Hadamard-based random projection, and I wedge a random projection in there, then I get relative error. And why is that? It's because you can think of this as a QR decomposition. Right? I wrote it as an SVD, but it's really a QR decomposition. If I take the exact matrix A and I do QR on A, if I post-multiply that by R inverse, I get Q, and I'm done. I do QR not on A, but on the projected version of A, and I post-multiply A with R inverse for the projected problem, and I'm almost done. I get an almost orthogonal matrix. In fact, I need to put a second projection in there to make everything fast. But if you do that, then let me just stop there. If you do that, what you get is you get your 1 plus epsilon. In fact, you have a sketch that's an almost orthogonal matrix. You can consider the dot products between different rows of this sketch, and you get all the off-diagonal elements. You can extend this to fat matrices, streaming environments, and so on. So you can actually check or test the hypothesis that your coherence is small, that your leverage scores are small, and little over orthonormal basis time. And that applies to arbitrary matrices. If you have correlated dictionaries, you give nice things or bad things and anything you like. So that, let me wrap up.